So, today let me consider another class of subclass of perfect graphs, which is, so this is in 22nd page. Okay, I will come back to comparability. So, what is comparability graph? So, you have all learned about relations and all, no? When what is a relation? If universe is given, let us say it is 1 to n, a relation, how is a relation defined there? So, on an n element set, suppose E, if A equal to the n element set 1, 2, 3, n, then you can take any subset of A cross A, right, Cartesian product of A, that will be a relation, because it will be pairs, right, say 1, 2, 3, 2, like that. Any subset you can take, even an empty set is fine, right. This is a relation. So, 1 is related to 2, 3 is related to 2, like that, right, or 4 is related to 5. So, that is a, so you do not need to have a connection explicitly mentioned. So, one is the double of other or something like that, then it will be clearer, but any subset is fine of this thing, but it comes in pairs. So, you can easily see that a relation corresponds to some graph. What kind of graph does it naturally map to? In its full generality, like it is the graph, directed graph, right, because a pair becomes an edge there, directed edge, an ordered pair becomes a directed edge. So, you can use this A as the set of vertices 1 to n, and then when you see 1 2, right, when you see 1 2, you can put 1 2 directed edge from 1 to 2, right, that will become a pair. So, the relation can be captured by these directed edges, but not that there can be edges of the form 2 2 4 4 and all, right. Then this will come like this, self loops, right. So, when there is an edge 2 comma 4 is there, it will be like this, right, 4 comma 2 will be like this. It is possible that both are available, 4 2 and 2 4, right, in a relation. So, you get put this, right. So, essentially what I am trying to tell is the way we saw relations defined on 1 to n, right, that can be mapped to the directed graph, right, the set of directed graphs, because if you get a directed graph, you can write down the relation corresponding to this, because for each edge that is a pair, ordered pair, this to this, that means that comma that, right, I comma j, I to j edge, and self loops mean one kind of things, reflexive map those things, and like that. And now you know that when you studied relations first, you might have studied equivalence relations and all, right. What is that? Equivalence relation, some properties should be there in the relation, that is the reflexive, symmetric and transitive, right. Reflexive means all those things like 1 1, 2 2, 3 3 should be there, right. And means a member is related to itself. So, in our graph it will correspond to self loops on all vertices, and symmetry means what? Yeah, if A comma B is there, B comma A also should be there. That means in a graph what will correspond to? Yeah, if there is an edge from I to j, you see an edge like this, then we should also see this, right, simple thing, right. A symmetric relation will see that kind of things everywhere, all edges will have both sides. It is like an undirected case, right, undirected case. And what is transitivity? That is the more meaningful one, or more non-trivial one, because it says something like this, I j, suppose I have this, and j k suppose I have this, then what should I have? Yeah, I should have this, right. Not only that, I j should be this direction should be correct, I to k, right. So, this is transitivity. So, can anybody guess what will suppose I get an equivalence relation and draw a graph corresponding to that, how will it look like? Because of this transitivity, self loops will be there everywhere. Apart from that, this transitivity and symmetry, right, it makes it impossible not to have an edge between. Suppose if I can reach from say 1 to 2 to 3 to 4, right, like this, then I will have this edge also. Why? Because this is here and right, and because of this and this is here. So, if I can reach like this, then this edge will anyway come. Why? Because this will come due to this and this, and once this comes due to this and this will also come, right. So, if something is reachable from a particular vertex through directed path, then that is directly reachable. That is what the direct edge should be. That is what transitivity implies, right, which essentially means that whatever is reachable will form a complete set, and symmetry is also there, no, because if I can reach from here to there, there to here also I have a path, because every edge can be reversed, right. So, therefore, those relations will simply look like some collection of complete graphs, right. There is nothing big with always a lot of self loops everywhere. So, that seems to be very trivial when it comes to graphs, right. We also know that reflexive, symmetric, transitive relations, that equivalence relations corresponds to partitioning and all, right. You recall that theorem, right. The set will be partitioned into a few disjoint sets, right. So, that is equivalence class. So, that partitions correspond to these things, right, because here the relation between any pair there is a relation, otherwise there is no relation between something from here and something here, there is no relation. This is what. But so there is nothing to study here. So, what we study is the other one, which you probably are more familiar with after this equivalence relation, namely what was it called? It was called a partial order relation. No, have you studied that? Partial order. Sometimes we use this word poset and all, right? Partially ordered set. Partial order. See, total order is a relation like 1, 2, 3, 4, and so every pair is like, you know, which one is bigger and which one is smaller, right, like that, right. So, everything can be ordered in one. The partial order means what? It is a relation, but it satisfies 3 properties. One is reflexive, right. That means every member is related to reflexive. Second thing is what? Antisymmetric. It is antisymmetric. Antisymmetric means what? In terms of graphs, what will it correspond to? Yeah, only one direction, I to j or j to I, not both, right, I to j or j to I. So, if you have a undirected edge, you can give only one orientation to that, either from I to j or j. You should not put both those things, like in the other case you put both because it was symmetric, right. But here we say that exactly one direction should be given, one orientation is only allowed. That is antisymmetric. Third one is again transitive. So, transitive we have already seen, right. So, the difference is only here, this makes a big difference, right, that makes it non-trivial, more non-trivial, right. So, now it does not mean that from I to j if I can reach through a directed path, it does not mean that from j to I can reach, right. So, that may not be true, right. So, that makes it more non-trivial. So, it can be possible that through a directed path I may not be able to reach from one vertex to another, even if it looks connected by its undirected counterpart, underlying undirected graph is connected, still you may not be able to reach through a directed path, relation may not be there. So, that is the partial order. So, now given any partial order, you can make a graph out of it, right. How do you do? Undirected graph out of it, just discard the directions, you get the edges. Some edges will not be there, some edges will be there, connected graph, because when the relation pair is there, you will have the edge, otherwise you will not put the edge. You recall between I and j, one of the directions only is allowed, right. I to j or j to a is allowed, not both. So, if I to j edges, I to j or j to I, any edge is there, you put that edge, just remove the arrow from that. But there can be things without an edge. So, those pairs which are comparable, that means there is a relation between them, right, then we put an edge, otherwise don't. Comparable means we can compare them, otherwise it is not possible. Suppose if you have a partial order, like something is a divisor of the other or something, it is a partial order relation, right, because 2 is a divisor of 4, 4 is a divisor of 12. So, 2 is a divisor of 12 also, transitivity is there and antisymmetry is there. If 2 is a divisor of 4, 4 is not a divisor of 2, and every number is a divisor of itself, right, it is reflexive. So, therefore, it is a partial order relation, and now this partial order relation if you get. So, there are many members like there is between which there is no relation either way. For instance, 2 and 3 if you take, neither is 2 divisor of 3, 3 is not a divisor. So, we cannot put an edge between them, it is not comparable, we cannot compare them, right. But then if you take 64 and 4, you can compare, right. So, 4 divides 4 to 64 is there, or not 64 to 4, right. So, but we can compare it. So, once you get a partial order, just get rid of the arrows from that and you get the underlying graph, that is underlying undirected graph, that is the comparability graph of corresponding to that partial order. Because the comparability relation is captured here, right, in which two members, which pairs are comparable. Now, the natural question which comes is, this is the way you define a comparability graph, a graph which is obtained from some partial order by deleting the arrows, deleting the directions, discarding the directions, the underlying undirected graph of that. We can discard the self loops also, that is unimportant fact, self loops are of no use. So, underlying undirected. So, that is the comparability graph. So, but there is another question which naturally comes then, given a graph, right. So, first you are given the graph now, and then you ask, is it coming from some partial order? The reverse, is it, so you can ask one, given a graph, oh, is this graph, do I have a partial order for that? So, how do I check it? Actually, I should be able to give direction to the arrows in such a way that all those properties are satisfied. That is okay. Reflexivity we can forget anyway, self loops you can put anywhere, forget it. So, the other two, antisymmetry, which that is also very easy, just put one direction, right. So, not that once you see it undirected, do not try to put two edges. For instance, if this is a triangle, here only put one, do not try to put this also here, right, not like that, only one direction you put, right. And now, suppose I give this direction to this edge, right. Then what happens is the third edge, so I try to give this direction, then what is this thing? That is fine, because this is transitive, right. And if you put this thing, that is also fine. But suppose I had given the other direction, some other direction, suppose I give this direction, 2 arrows, Now, the third edge is having this direction, right. Okay. So, but on the other hand, if I had given this this direction, what would have happened? Yeah, this is not transitive, right, because this direction should be from here to here, right. So, you have, but you have to just check, you have to try whether you can give arrows, then you can satisfy all the three properties, and that becomes a partial order. So, it will correspond to a partial order. When you write down the pairs correspond to the directed edges, that will become a partial order. This is a simple graph, and now let us look some other case of, suppose it is suppose I start giving this arrow here. Can I give the arrow here now, just like this? If I give that, the problem is then transitivity demands that I should have this here and the arrow should be like this, right? But then that is not there. So, therefore, yeah, the edge itself is not there. How can I give direction, right? So, therefore, what can I do? So, if I say that, oh no, this is not a graph which I can transitively orient. No, the thing is that you can in fact give this direction, then this problem will not come, right, because nobody is demanding now, right. It's still the transitivity is vacuously true, because nobody is A, B, B, C kind of thing hasn't come. But when I go here, then I should be careful not to put like this, right, because if I put it, then there will be a demand for this, but that is not there, therefore I cannot put it. So, therefore, we should put it like this, and here it should be like this, here it should be like this, and the last one should be like this. So, it is transitively oriented, right. Though there is actually no three such things, A, B, B, C kind of thing has never come. It is vacuously true that transitivity is true, right, because there was no such A, B, B, C, right, which demanded to have a C. So, we carefully avoided it. So, therefore, these cycles are transitively orientable. Therefore, they are coming from some comparability graph. It's a comparability graph because it is obtainable from a partial order, right. Partial order can be obtained by writing down all these pairs, right. It is partial order because it satisfies all the reflexivity, antisymmetry and transitive conditions. But this is not always so, because if you had just increased one more, suppose I was only keeping this is a 5 cycle, odd cycle, the other was even cycle, right. Here there will be a problem. Why? Okay, the problem will be, suppose if I give it here, I know that I have to give it now like this, and the next one has to be like this, next one has to be like this, and here what will I do for this edge? Which direction is valid? If I give it this direction, then you see this will be required, but that is not there. But if I had given the opposite direction like this, then this will be required, right, because like this edge will be required, that is also not there, right. Both are not available. So, this cannot be given, that is a conflict. The conflict came because it is odd length. If it was even length, nicely it would have adjusted, right, like last time we had seen, left right like that, reversing, and it would have nicely here. In fact, yeah, it's when I am giving the direction demanded by this side, here it is a conflict. So, therefore, that is not a comparability graph, because that graph cannot be obtained from a partial order by removing the orientations on the edge. It is not the underlying graph of a partial order relation. So, this is what is comparability graph. So, I can give you a couple of more examples. There is a bull graph. I don't know whether it is required or not, but let us see. bull head graph. It's drawn like a bull head, you know. So you can start giving. So this is just for systematic analysis. Just try giving some edge. So it can be here like this or the other way, right? So try like this. Suppose this is the direction I give. So should I use another color here? Okay. Suppose I give a color, give a direction here. Now the direction of this edge cannot be this, right? Because then from here to here I should have an edge, right, but that is not there. So therefore it has to be like this. It is true because there is no edge connecting the end point, so that has to be. Now what should be this? This same thing, it should be like this, right. Now what should be the direction of this? If I put it inward, that is fine, but if it both are fine, right, but then yeah, here this edge I can tell, because I cannot put like this, because in that case I will need this edge from here to here. So this should be like this, and the next one would be opposite side, right, and this one also I can tell, then this should be like this, okay. And then can I tell what should be this? Because it is going like this, should be like this, because otherwise from here to here I will need connection. And now what happens? So if I give this direction here, then this, right, because here I have problem, right. So I cannot give that direction, so I should give this direction, but if I give this direction, so okay, you try to do this thing. I hope you understood what I am trying to do, right. So the question is, sometimes you can prove that like that contradiction comes by trying to fit it. So sometimes some edges will not be, so both the direction will not be possible for finally for an edge, and then that means it is not transitively orientable. Sometimes everything can be oriented without any conflict, then that is partially orderable, right. This is the definition of the partial. This was a bit more difficult to understand than the earlier ones, that is why I told you. So I took this much time to explain it. So I hope you understood what is a comparability graph, right. So now I will explain. So because we all started with the perfect graph thing, right, chi perfection and alpha perfection, we will just look at the comparability graphs, these 4 parameters, and establish that this chi perfection and alpha perfection exists in comparability graph, and connect it to some well known stuff. So look at chi perfection first. Look at chi perfection first. Chi perfection. So when you talk about chi perfection, okay, one thing we will clear first itself. Take suppose you are given a comparability graph. Now take an induced subgraph of this comparability graph. Do you think it will be a comparability graph, or can it be a non-comparability graph? Opinion? It should be, because if you have oriented the entire graph without conflict, and if you take an induced subgraph, you can just retain that same orientation, right. Because if there is a conflict when you deleted some vertices, that conflict would have remained otherwise also, right. Transitivity is broken in an induced subgraph, in the bigger graph also. So therefore comparability graph is also hereditary, in the sense that that property is hereditary. So any induced subgraph will retain the comparability property. So therefore we can talk about generally comparability graphs, whether chi is equal to omega or not, that is what we will ask. Chi means chromatic number, and omega means C. That is about chi perfection. Chi perfection, what is the biggest clique number? What kind of things translate to cliques? Means all, if you take certain collection of members from the set universe, that means the vertex set. So they all should be comparable with each other, right. So, each will be saying that who is bigger and who is smaller, or maybe the relation will be there, right. So, what kind of order is that then is restricted to that induced subgraph? It is called a total order, though the entire thing is a partial order. So, if the clique, the vertices which are forming a clique, which are inducing a clique in that partial order, right, corresponding to that order will be the order in that restricted to the partial order restricted to that set of vertices should be a total order, right. That means in the partial order terminology it is called a chain. Why is it called a chain? So, in the less than equal to relation in natural numbers, so we say 1, 2, 3, 4, 5, etc. is a chain, because we can order them like this, right, one after the other, or any subset of natural numbers if you give me, then I can order them as a chain, because there is the smallest one and the next smallest one, next smallest one. In the partial order that is not possible, some of them are not comparable, right. So, in the total order you can always do that, not necessarily less than equal to relation, you can always have this minimal one and the next one, like that you can order, right, because it is totally ordered. So, that is the so therefore, it is a chain. In the complete graph will correspond to a chain, right. So, in the partial order you can identify some lowest element and then something. So you do not need to be surprised about it, because you know the transitivity says, yeah, this all the edges are there, right. Because of the transitivity only it becomes a clique. Do you understand what I am telling? Do you follow what I am telling? Suppose you have a chain, then because of the transitivity all pairs will be connected, right, because you have a path from anything to one to the other. So, therefore, by transitivity you will have an edge between them. So, that will form a clique. On the other hand, if you get a clique, you can, because it is a partial order, right. So, you can find out between any two, for instance, which is smaller, and then yeah, you can if there is an incoming edge into that, right, you can track backward and then you will get so there cannot be two smallest one, right, because if there is a two smallest one, there is a relation between them also, right. So, I cannot say that this is also smallest, this is also smallest, but then what will happen to the edge between them? There should be a direction between this, and so there should be one of them should be smallest. So, therefore, you should. So, the clique correspond to this total orders inside the partial order, that means chains, right. The longest chain will correspond to the clique, Now, I want to show that, so this is the maximum clique, then I want to show that if you want to color the partial or this comparability graphs, I need only that many colors. So, I hope you understood what is the maximum clique in this thing, right. And now, if you want to color, can anybody tell me a strategy to color the vertices of the comparability graph, that is the graph coming from the partial order, with a maximum of, you should not use more than the maximum clique number of colors, right. So, and recall the maximum clique is essentially the longest chain, the longest in the sense the chain containing the maximum number of vertices, right. So, you should only use that kind of a thing. So, what should be an algorithm for that? Can you guess the coloring algorithm here? A coloring strategy, let us say.